This is RL series AC circuit. Here this is the resistor R which is connected in series with this inductance L, and both are connected with this applied voltage. And here we know that in the series combination of the components the current is the same and the voltage will be different. Here the voltage of this resistor, which is given by V of R, and the voltage of this inductance, which is given by V of L, will be different. Okay, and if we add them, it will be equal to this provided voltage, this alternating voltage. Okay, so we do not add them directly by applying the simple algebra rules. Okay, because we denoted these voltage, these alternating voltage, in the form of the phasor diagram. So in the phasor we will have the behavior of the vector. Please remember here that the voltage by itself is not a vector, but for our convenience we represent that in a vector in the form of the phasor. Okay, so from there we know that the current, when the voltage is passed from the power resistor, the voltage and the current are in phase with each other. Here the angle is 0, and when this voltage is passed from the power inductive and for the power inductive circuit, so in that case the current lag behind the voltage by 90 degree, and we had discussed this in the previous videos. So here the current is the same because in the series combination of the components in the circuit, the currents are the same. The same current is passed from this resistor and this inductance L. So therefore we consider this current as a reference. Okay, so here I have considered that current as a reference. Okay, and now we will add the phasor, mean the vector, a vector representation of this voltage, which is VR, and this is actually the vector, which is VL, and we will add them. So we do not add them by simple algebra, we will add them by applying the vector algebra here. Okay, so the vector algebra for the addition is the head to tail rule. Okay, so we will add these two voltage by head to tail rule. Okay, so first I am going to take this voltage, which is V of R. Okay, and here I have selected that. Okay, this is V of R, which is actually this. Okay, and as we know that in the head to tail rule we will put the tail of the second vector. Okay, here I am going to add this V of L with this V of R, so we will put the tail of this second vector with the head of that first vector. Okay, so here I am taking this vector and bringing that to here. Okay, this is that same vector. Okay, and the tail of this vector we will connect with the head of this final vector. Okay, so this is actually this vector. Okay, now from head to tail rule the resultant will be we will draw the resultant line from the tail of the first vector, and we will connect that with the head of the last vector. So this is actually the resultant, and here the resultant is actually this provided voltage. Okay, so we have added these two, which is this is actually the resultant, and which is actually the addition of this VL and V of R. Okay, so we add the phasor diagram of this vector, the phasor of this V of L and V of R, and which is given by this V. Okay, so this is actually the 90, it make the right angle triangle. So here this is the 90 degree, so we can apply the Pythagoras theorem and we will find this voltage. This is the hypotenuse, this is the perpendicular, which is present parallel with this angle. Okay, that is actually the perpendicular, and the adjacent side with this angle is treated as the base. So this is the base, and this is actually the perpendicular, and this is the hypotenuse. Okay, so according to the Pythagoras theorem, the hypotenuse whole square is equal to base square plus perpendicular square. Okay, so we will put the values here. So here this is the hypotenuse, and which is given by v, and v, okay, which is square, is equal to the base, which is v of r, and whole square, plus the perpendicular, which is actually this v of l whole square. Okay, so I am going to put the value. So this is actually the v square, and here this v of r is equal to ir. So we will put the value of that ir square plus this x v l is equal to I x cell whole square, and here this v square is equal to I square r square plus I square xl square. We will take the common I square from this, and here this will become v square is equal to I square, and here the r square plus xl square. So we need only the voltage value, so therefore we will take the square root on this. So then this will become here this, okay, square root of this, which will be equal to v, okay, and on that side the square root will be remain. Okay, so therefore it is become I square and r square plus xl square. Okay, and here the square root on both of them, so therefore v is equal to square root of I square and square root of r square x plus xl square. Okay, and this square root and this square will be cancelled, and the final equation for that is v is equal to I, okay, and square root of r square plus xl. Okay, this is actually the magnitude. This is actually this equation 1 is actually the magnitude of this voltage, okay, and which is given by the Pythagoras theorem, and which is equal to this. Okay, and from here this r square plus xl square square root is equal to v by I. Okay, and from the Ohm law, r is equal to v by I. So this is actually the resistance upper by both the resistor and the inductor. So when there is the resistance from the combination of the resistor and the inductor, we call them as impedance. So this is actually the impedance here. Okay, this is the impedance. We call this as a impedance, and which is denoted by Z, and from here we can write as Z is equal to V by I. Okay, this is the impedance, and this is actually the opposition upper by this resistor R and the inductance L to the applied voltage. Okay, so this is the equation 2, and which denote the resistance upper to this voltage, and this denote the magnitude of this voltage. Okay, and this and here the resistance will be occur to that voltage, and which is given by this Z. Okay, now we will find this angle theta, okay, this phi. Okay, so for that we have the tangent theta, and which is given by this. Okay, tan phi is equal to perpendicular by base. So here in this case perpendicular is V of L and the base is V of R. So we can put that here, VL VR, and the value of VL is IXL and the value of VR is IR. So instead of this we will put IXL divided by, this is actually the reactive inductance, okay, and divided by IR. This is actually the resistance from the resistor. Okay, so this I and I will be cancelled, and the final equation for that is XL divided by R. Okay, so this is actually the relation for tan phi, which is equal to XL divided by R. So from here we know that if we divide this tan alpha on both side, so here we will divide that tan, which is equal to XL divided by tan R. Okay, so this tan and this tan will be cancelled, and here only the phi will be remain on this side. Okay, which is equal to, and when this tan is go here to the denominator, okay, so this will become tan inverse, okay, and into XL by R. Okay, this is the final equation for the phi and the phase difference present between this V of L, the inductive reactance, and the voltage, the voltage that pass through the resistor. Okay, this is actually the phase difference between them. Okay, so first we determine the magnitude for this voltage, then we determine this phi. Okay, and after that we determine this the impedance, the opposition upper to the flow of charges in this circuit, which consists of the resistor R and the inductance L. Okay, so here is in this diagram we will apply these all concept. Okay, so first here this is the voltage V, and which is equal to Vm sine omega t. Okay, so when this voltage is passed through this resistor, okay, that voltage will be leading the voltage of the resistor. So the question arises here, by which degree it will lead the voltage of the resistor. So that degree, that phi, that angle is given by this angle. So the voltage of the provided voltage will be leading the voltage of the resistor by this angle. Okay, and this angle is given by tan inverse, and we know the reactive inductance of that inductor and the resistance of the resistor. So if we divide that and take the tan inverse, we will determine this phi, and here this voltage is leading the VR by that same phi. Okay, so how we determine that this is leading, why this is not lagging? So that information is come from this diagram. Okay, So here this is V of R. Okay, this is V of R, and this is actually that resultant voltage. So here from this phasor diagram, this V of R is lagging and this V of L is leading here. So this V of L, so this V is leading this V of R by this phi, and which is given by the tan theta. Okay, and similarly when that same voltage is passed from this inductance L, now in this case this provided voltage will be lagging from the voltage of this inductor VL. So this information is also given by this this diagram. So here in this diagram, as we see here, the V of L, okay, this is actually the V of L and this is actually the provided voltage. Okay, so here we can put this phi here. So if the phi is present here, so then the voltage will be given by just like, okay, the voltage will be this. Okay, so here in this case the voltage is here. Okay, this voltage will be here. Okay, and this is actually the voltage of the inductor. Okay, and that voltage of the inductor will lead this total voltage, okay, which is provided to this circuit. So here this is lagging behind that. So therefore I have here this I denote here that this V is lagging from this V of L, which is lagging from that V of L. Okay, so now when these two effects occur, so we have also the current in this circuit, and that current is actually given by here from this phasor diagram. We know that this voltage is leading the current. Okay, this is leading the current I, and here we have that current. Okay, we take that as a reference, and this voltage is leading this current. Okay, so the current is on the x-axis, and this voltage it is making some phi with the x-axis. So therefore this current is lagging behind that voltage. So here I have draw the graph for that. This current is lagging behind this voltage. This voltage start from here, and this current is lagging from that by the angle phi. Okay, so that phi is given by the tan phi, okay, which is perpendicular by the base. So here I am going to recap all these. The all concept is present here in this diagram. If we provide the voltage will be leading from this resistor. Okay, from this voltage of this resistor, and here this voltage will be lagging from the voltage of this inductor. Okay, and how much it is leading or lagging, which is given by this phi. Okay, and when this voltage, okay, that falls from this component and also from this component, and here we will have some current and voltage, and in this case that voltage will be leading this current. Okay, and which is also given by this phi. Okay, and here in this phasor diagram, this is on the x-axis, this current, and the phase, the voltage is making some angle phi with the x-axis, and here this is leading this current. So therefore I have made this. Okay, so so from here we know that V is actually a sinusoidal function, and we can write that is V is equal to Vm sine omega t. Okay, V is equal to Vm sine omega t, and this is, let's say, equation 1. And here we know that this V is this current I is lagging behind that current, so the resultant current in this circuit will be lagging behind the provided voltage. So therefore the I in this case is given by this I is equal to Im, okay, sine omega t minus phi, okay, minus phi. This is lagging behind the voltage by this phi, and which is given by, so here it means that this current is lagging behind this voltage by this phi, okay. So this equation 2, let's say this is the actually the resultant current in the circuit, and this is the resultant this is the provided voltage, okay. So here these both are making an angle phi with each other, and this current is lagging behind this voltage, okay. This blue color graph is actually for that resultant voltage, okay, and here this is the resultant current, okay, and this current from the phasor diagram is lagging behind that resultant voltage. So here this is lagging behind that resultant voltage. So by how much degree this current will lagging behind this voltage, and that is given by this, okay. This phi is equal to 10 inverse XL by R, so that is actually that phi. So the phase difference between this voltage and this current is this phi, and here is that same phi, okay. So at each and every position that phi will be the same, okay. So here I'm going to zoom this, okay, and this is actually the graph, this is actually the graph for that voltage, this is the graph for that current, and here is the phase difference, okay, this phi. And here we know that if we have this current, okay, and we have this voltage, and we know the formula of the power, which is equal to V multiply I, okay. Here this I the current is negative, and this voltage is the positive. If we multiply negative with positive, the resultant will be negative. So therefore here this yellow shaded region is in the negative side, okay, and it gives us the information about the power, okay. Here both the current, this is actually the current with the red color, and here this is the voltage, both are the positive and having higher values, higher amplitude. So if we multiply that amplitude at each and every degree here, so if we multiply that, it will give us the resultant power, and this shaded region is that resultant power. Here this current is positive, this voltage is positive. If we multiply positive with positive, the sign will be the positive, okay, and their amplitude is here will be multiplied with each other, and this will be the resultant power here, okay. So now from here to here, okay, this is the current, and which is the positive, and this is voltage, which is the negative, and if we multiply that positive with negative, the resultant will be the negative, and here this power will be the lower side, in the negative side here, okay. And their magnitude, by how much this power is below this mean position, so that is given by the multiplication of the amplitude of the current and the voltage at each and every degree, okay. And here in this case this current is negative, this voltage is also the negative. If we multiply negative with negative, the resultant will be the positive, and here this is the positive, okay. This is actually the graphical representation of the power, okay, which is the positive. And here if we multiply the amplitude of this current and voltage at each and every degree, so it will give us some data point, and if we plot that, it will give us such a type of the power. Okay, now we are going to determine the power factor here. Okay, the power factor. So for that, let's consider this graph. In this graph is actually for the power. Okay, the power in this side of the phasor diagram we have the voltage. Okay, and here we have the apparent power. On this side we have the VL, the voltage of the inductor, and here we have the reactive power. Okay, reactive power, I will give the example for that. And here on this side we have the what we can say, this V of R, and here we have the true power. Okay, so what is the difference between the apparent power, the reactive power, and the true power? Okay, so the apparent power is actually the total power provided to the circuit. Okay, so when the total power is provided to the circuit, here in this side we have the inductor having inductance L, and we know that if we provide the voltage to inductor, the current will start in that inductor, and that current will change in magnitude and direction, and due to which the change in magnetic field will be occur. So some sort of the power will be released in the will be dissipated in the form of that magnetic field. Okay, so that dissipation of the power in the form of magnetic field is called the reactive power. So on this side we will have the reactive power. Okay, on this side we have the true power. So let's discuss more about the power. So here I am going to take the topic here is a power. Okay, this is the power, and we know that the formula of the power is P is equal to I, the current, and V is the voltage. Now in this case you may think about which voltage we will take here. So the voltage we will take is this resultant voltage, and which is given by this. Okay, and the current we will take this. Okay, and here in the phasor diagram the current is this, and here the current is lagging behind that voltage. Okay, and we will take the values of that here. Okay, so we know that let's say this is the power, the equation for the power, and we know the power through resistor. Okay, in the power through resistor, which is given by P is equal to I V cos, let's say cos theta. Okay, cos theta, and let's say this is the I and V. Okay, and in the resistor we know that the current and voltage are in phase with each other. So therefore this angle will be 0, because the current and voltage are in phase with each other in the in case of the resistor. So therefore it will become I and V. Okay, and here we have some power factor, but in case of the inductor L, which is equal to IV cos of phi theta, and here IV cos of 90 will be present, because this in case of the inductor, okay, the voltage is leading the current by 90, so therefore it is equal to 0. Cos 90 is equal to 0, so here the power is 0. Okay, so from here the average power, the average power is given by this power of the resistor, okay, and the power of this inductor. So the power of the inductor is 0 and the power of the resistor is given which have some value. Okay, so the power is present there, so therefore I put the generalized expression for that, which is equal to I v cos phi, and divide in average we divide that by this will be 2. Here we have 2 measurements, so we have 2 expression, so it is equal to I v cos phi divided by 2. Okay, here instead of this 2 we can write this, so IV cos of phi divided by, instead of that 2 we can put square root of 2 and square root of 2. If we if we multiply these two, it will give again this 2, so therefore I write here. So from here we can write that P is equal to I divided by 1 square root of 2 and V divided by this remaining square root of 2 into cos of phi. So I by square root of 2 is actually the RMS value, so P is equal to I RMS and V RMS into cos of phi into cos of phi. Okay, so this is actually the IRMS and VRMS is actually the power, okay, and which is given by this, the apparent power. So this apparent power, the total power provided to the circuit is given by this relation, which is equal to power. Okay, so that apparent power we can say here, this is actually the apparent power. Okay, the apparent power, and which is equal to IRMS and VRMS into cos phi. Here this cos phi is called the power factor, which is equal to the power factor. Okay, and we know that the cos phi, okay, cos phi is equal to base by hypotenuse. For the cos, we know that cos theta or the cos phi is equal to base by hypotenuse. So therefore in hypotenuse here we have the apparent power, apparent power divided by, on the base we have the true power, the base we have true power. Okay, so we can write here as a true power, and on the hypotenuse we have apparent power. Okay, so the true power here, so the true power by apparent power we call that as a power factor. So therefore here this cos phi is the power factor. So this is the final relation for the apparent power. Okay, so this much power will be present in the circuit. Okay, now I am going to analyze this power. This power is mentioned here by the yellow color, and this shaded regions, okay, is actually that apparent power. Okay, this is actually that apparent power, this shade regions, which is equal to IRMS, which is given by IRMS VRMS into cos of phi. Okay, and that phi is actually the phase difference between this voltage and the current. Okay, so from here we know that in this section, in this quadrant, the power is negative. Okay, and in this section the power is positive. So when the power is the negative, it means that the power is delivered by the circuit to the source. Okay, and here when the power is positive, it means that the power is delivered by the source to the circuit. Okay, and here This is again the negative, and which is the power delivered by the components of the circuit to the source, and here is the power delivered to the component of the circuit by the source. So by combining all these power, the resultant will be the positive, because here these negative areas are less and these positive areas are more. So from here we conclude that in the RL circuit the power will be delivered, the more power will be delivered to the components of the circuits, okay, and the less power will be again given by that component of the circuit to the source. So here the resultant power is actually the power dissipated, okay, the power dissipated in the circuit, in the component of the circuit, okay. And this was the explanation about the RLC circuit, the RL series circuit, okay. So this was the in-depth intuition of the RL series AC circuit, and this all about from my side, and that's it guys. Thanks for watching.